Okay, so here are the answers to the free body diagram practice. As you're going through these answers, you might want to pause between each one so you can go through the answers as you're doing the questions and make sure that you're getting it correct as you're going. So let's look at number one. Number one is a book sitting on a table. So I draw my square with the dot in the middle of it. Now there's two forces acting upon this book. First, there's gravity pulling straight down on it. So I put F gravity. And there's also a force acting up on it. That's the force from the table. Now, anytime an object is sitting on another object, we call that the normal force. And because it's just sitting there, it's not moving, it's not accelerating, it's at a constant speed, which is 0 meters per second, the line has to be equal in length. So I call this F normal, and it has an equal length line pointing up. All right, the second one, a skydiver falling at a constant speed. Same principle here. So we have a box with a dot in the middle of it. Gravity is pulling the skydiver down. So I label F gravity. Now this time there's not, the skydiver's not sitting on anything. He's just going through the air. But there is air resistance pushing back up on him. And because he's going at a constant speed, the arrow is going to be an equal length. So I would put F air resistance or F friction. Either one works, just as long as I'm labeling the force there. So that's number two. Number three, a plane excelling across a runway, but not off the ground yet. So here we go. We've got my box with the dot in the middle of it. It's sitting on the ground still, so it's got a normal force acting on it, and there's gravity still pulling it down. So I have gravity, I put F gravity, and there's also, like I said, there's that normal force. Now, the plane is not going up and down yet. It's at a constant altitude. Since it's not lifting off the ground, the normal force and the gravity force will be equal in length. Now, if the jet were taking off and it were actually lifting off the ground, then the force pointing up would be greater than the force of gravity because it'd be accelerating in that direction. But it does say in this question that a plane is accelerating across a runway. So as it's going across a runway, we draw an arrow, and that's going to be called thrust. That's pushing it forward, so it's thrust from the engines. You could just call it engine or whatever you wanted to, but it's called thrust. So we'll put F thrust going forward. And now there's a frictional force acting on it as well, because anytime that we're talking about things happening here on Earth, there's always going to be that frictional force. However, it's accelerating, so the frictional force is going to be less than the thrust force. So I'm going to draw a shorter arrow for friction. This diagram shows me that the up and down are equal in length, so it's not going up or down, but the forward thrust is greater than the frictional force, so it's going to be accelerating forward. All right, number four, an ice skater moving at a constant speed with no friction being applied. This one's a little tricky. So we have an ice skater, so apparently they are standing on some ice. So there's a gravitational force acting on it. So we have F gravity. It is on an object, and the skater's not falling through the object, or it's not being pushed up in the air. So we have the normal force. And now it says there's no friction, so I don't draw any arrow for friction. And it says it's moving at a constant speed. Well, since it's moving at a constant speed, that means the arrows would have to be equal length. Well, since there's no friction, there cannot be any forward push on the ice skater either, because they're just moving at a constant speed. If they were accelerating, I would put an arrow there, but just constant speed. So in this case, with no friction, there's no forward motion either. No forward push, I should say. And so that's number four. All right, let's take a look at number five. You're pushing your friend down a hill while they are on a skateboard. They are accelerating. So this one's a little tricky as well, because now all of a sudden, if we visualize this, they're going down a hill and the hill is angled. So here you have your friend on the skateboard, and right? So they're just having a blast going down the hill. And so now, let's draw this one. I draw a box. There's still a gravitational force, and that is going straight down. But the normal force is not going straight down. Because the person is sitting on the angle, the normal force always goes at a right angle or 90 degrees to that surface. So my normal force will need to point at an angle to show that it's 90 degrees to the surface. So now I draw F normal at an angle. So there we go, we have our F normal, it's at an angle. It's still the same length of gravity because they're not falling through the ground. And then it says they are accelerating. So there is a push force that was applied that's causing it to accelerate down the hill. So since it's down the hill, I'm going to put it at an angle. So now I have push force, so I push F push. And then there's always a frictional force unless it states otherwise. But since they're accelerating, my frictional force is also going to go in the opposite direction of the push. And it is going to be a smaller arrow. And we'll call that F friction. So there's number 5. And then let's do our last one, number 6 here. An apple accelerating to the ground with no air resistance. So once again, I draw my box. Gravity is pulling the apple down. So I put F gravity. It is accelerating. So the gravity has to be longer than any arrow that's pointing up. In this case, there would be air resistance, but it specifies in the question that there's no air resistance. So this is all you draw for an apple accelerating to the ground.